times cosine beta x plus I times the sine of beta x. Now, we could derive this later. Let me write that out more clearly. So we have e to the alpha x cosine beta x plus I e to the alpha x sine beta x. This is what, e to the alpha plus I beta times x is equal to. So for us, at the moment, that's a definition. I'm sorry, I shouldn't say proposition just yet. This is definition. The proposition I want to make for you, here's the proposition. ddx of e to the lambda x is equal to lambda e to the lambda x for lambda in the complexes. Now, you might be like, whoa, 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 whoa. Nobody taught me how to differentiate complex valued functions of x. But you've had calculus 3, so actually you've already done it. The way we differentiate a complex valued function of x, what would that be like? So here's one. We could say, side note, I could have r of x equals to, I don't know, x squared plus 3ix. If I calculated dr dx, what would that be? Okay, fine. We differentiate, we differentiate ddx of the real part, and then the imaginary part like that. So in Calc 3 we use the notation x squared comma 3x, or maybe we use t instead of x, right? Does that make it more better? Here, I'll put some t's in here. Oh, too much. Oh, fine, you got me. I need to give you a definition. Yet another definition. I've neglected to give you a definition. Here's the definition. For u plus iv, which is a function from the reals to the complexes, we define dx of u plus iv by du dx plus I times dv dx. In other words, if we're taking the derivative of a complex valued function of a real variable, we simply differentiate the real component, and then we differentiate the imaginary component. We do them separately and add them together. This is how you do it. It's the same way you took derivatives of space curves in Calc 3, component-wise. It's just that. And that's the sense in which I'm differentiating this complex exponential, right? Because here it is, ddx of e to lambda x, what's that going to be? Well, and so here I'm gonna put lambda alpha plus I beta, yeah? Since I've introduced that labeling. So here you go. We've got e to the alpha x cosine beta x plus I e to the alpha x sine beta x. We got to do this differentiation. You'd like me to do this here, because if I don't do this here, it becomes one of your homeworks, right? Should I keep working? Yes, okay. Just checking. So this is ddx, and by homework I mean your next quiz, e to the alpha x cosine beta x plus I ddx. This is just the definition of how we differentiate complex valued function. Like that. We got product rules and chain rules. Oh my! It's very producty and very chainy. So we got alpha e to the alpha x cosine beta x minus beta e to the alpha x sine beta x plus I times alpha e to the alpha x sine beta x plus beta e to the alpha x cosine beta x. And, you know, there's an e to the alpha x in absolutely everything here, isn't there? So what can we do with that? Let's just bring it out front to keep it out of trouble. You know what? I don't like to bring it out front. I want to put it over here. It just feels like it belongs over there to me. I could be wrong. I'm going to regret my choice. It's done. What's done is done. What are we left with? We've got alpha. Let's group the cosine beta x terms, right? So we've got alpha from this one. Where else do we have cosine beta x? Over here, right? So alpha plus I beta cosine beta x, right? And let's see here. Oh, I've got an alpha sine beta x here, right? So let's say, oh, but there's an I. So plus I times alpha sine beta x, yeah. So that's just that term. What else is there, though? Minus beta is what in disguise? This is where you need a little imagination. Minus beta is I squared times beta, all right? So what I'm going to do is I'm going to take one of those i's and I'm going to put it out here. And I'm going to take the other I and put it in here. Does that make sense? And that's coming from this term right here, yeah? Hey, there's a common term here, isn't there? Look at that. Alpha plus I beta, also known as lambda. Lambda. So we got ourselves a lambda times cosine beta x plus I sine beta x times e to the alpha x. Well, finally. And if you could actually see that, what you'd see here is that we have lambda, I'll write it the other way, lambda e to the alpha x times cosine beta x plus I sine beta x, which is just what I defined to be what? Lambda e to the lambda x, yeah? Any questions? So what that means is all of the calculations I've thus far done for real lambda equally well transfer over to the complex lambda. Right? So it's still that, my claim would still make sense if lambda was equal to alpha plus I beta. Right? So, for example, if I had d squared plus 4d plus 5 squared acting on, let's say, z, because I'm thinking z being complex for a moment, if you don't mind. Then this is d plus 2 squared plus 1 squared acting on z equals to 0. And at the moment, in our current development, here's how we want to look at it, all right? This I could factor, actually, that's d plus 2 minus I times d plus 2 plus I. That's how this right here factors, right? But then I've also got that square. So when I square the factorization, I just square this and that. Yeah? So there you go. I mean, that's the factorization. Now, this is not a real factorization of the operator, right? This is a complex factorization of the operator. But my point to you is the calculus we did today still makes sense. So I can write down a complex solution set. What's the complex solution set? Complex solution. We have z. So we have lambda is -2 plus I, and that's lambda 1. And also lambda 2 is -2 minus I, right? And they're both repeated. So the solution set would look like, C1 e to the -2 plus I x plus C2 x e to the -2 plus I times x, C3 e to the -2 plus I times x, plus C4 e to the -2, I'm supposed to put minus I, sorry, on the last two, minus I times x, and I lost my x. There you go. I mean, this would be the general complex solution to the given differential equation, where C1, C2, C3, and C4 would be taken to be complex numbers. This is the general complex solution. But the thing is, that's lovely, but this is not what we're interested in. We want to find real solutions to differential equations. So this is, I mean, great, wonderful, but not what we're after. So the question is, how do we take this complex solution and extract from it what we want, which is the real solution? Right? So the way to do that, it's pretty, there's a standard way, and it rests on the following observation, which is that if we have L acting on Z, right, we can say that's L acting on the real part of Z plus I times the imaginary part of Z. And because L is a linear differential operator, what do I get? I get that this is L acting on the real part of Z, and the I pulls out because it's a constant, L acting on the imaginary part of Z. Right? Now, if we've constructed Z to solve L of Z equals to 0, then we have, in total, we have that, 0 is equal to this, right? So 0 is equal to that. But when you have 0 is equal to a complex quantity, what does it give you? Like, if it gives you that both the real and the imaginary part must be 0, right? So through this simple little calculation, we find out that both the real and the imaginary part of a complex solution are separately real solutions to the problem we're looking at. So what we're going to have to do next time is we're going to have to figure out a way to find the real and imaginary parts from these solutions to construct the solution that we want. It's really simple. It's almost already on the board. This right here is the real part of, e to the lambda x. This is the imaginary part of e to the lambda x. And when you have x times it, you just multiply by x, essentially. Those are actually the solutions right there, the real solutions. Exponentials times sines and cosines. But I'll work that out in hopefully more clarity next time. Once we've done that, that is the solution to the nth order constant coefficient differential equation in all of its glory. And then we'll go on to solving non-homogeneous problems, which is using this. And of course, applications. Yes, yes, yes. Thank you for your quiz.